Dear students, in this video we will learn about lattice planes in the three types of cubic crystals, namely primitive cubic or simple cubic, body-centered cubic, as well as face-centered cubic. And also we will discuss about how to calculate the interplanar distance ratio, which is a characteristic of each lattice. So what are lattice planes or crystal planes? We know that a crystal consists of a large number of planes which are parallel as well as equidistant. See, these are the two aspects of crystal planes. There are so many crystal planes which are parallel, and the distance between two consecutive planes is equal everywhere, so they are equidistant. And these planes are passing through the lattice points or the motifs, and also they are parallel to the crystal faces. In the previous class we have learned that the crystal planes are represented using V's indices, or more appropriately Miller indices, that is HKL. Now going to the representations of various crystal planes in simple cubic lattice or primitive cubic, which is popularly abbreviated as SC. You can see that there are three different lattice planes in primitive cubic. They are 100 plane, 110 plane, as well as 111 plane. How we distinguish these three, or what are the differences here? See, if you consider 100 plane, for example, consider the three crystallographic axes. Suppose they are here, like X, Y and Z. This is X, this is Y, and this is Z axis, and this is the origin. Then the plane which is shaded here, that is this plane which is shaded, you can see that from the origin this plane is intersecting along one of the axes, say it is Z here, and it remain parallel to X as well as Y. So the intercept here is, for example, it is 1A, it's A, or the coefficient is 1. So and since it is remaining parallel to X and Y, the intercept is taken as infinity. So it is 1, infinity and infinity are the V's indices, and taking the reciprocal, Miller indices become 100. So this is 100 plane. And remember that this plane is not restricted to this unit cell alone. It will continue, like, see, this plane will extend all the way, okay, and this plane is spreading out to all the unit cells. And also, if you take, instead of 100 plane, suppose I am marking another plane, suppose this plane. What about this plane? This is intersecting Y axis and remaining parallel to X and Z. Then it will become 0, 1, 0 plane. It can be also 0, 0, 1 plane. That means 1, 0, 0, 0, 1, 0, 0, 0, 1 are all equivalent planes. No difference. Now coming to the second one, that is 110 plane. See, I am drawing a plane, another crystal plane in a different way. You can see this is only one unit cell is shown here, and marking this plane passing through these lattice points or the motifs. Suppose I am taking origin now here like this. This is origin. You can see that this plane is intersecting two axes, these two, and remaining parallel to the third one, that is this one. So the intercepts are 1, 1. The unit cell dimension, suppose this is A, this is also A. So the intercepts are 1, 1 and infinity. So taking reciprocal, it will become 1, 1, 0. Coming to the third one, I am drawing a plane like this here. You can see. Suppose I am taking origin now here. You can take origin in any convenient way. Suppose it is taken here. You can see that this plane obtained by joining these three particles at the corners. Of course, this plane is not limited to this unit cell alone. It will extend to all the sides into other unit cells, so that the crystal plane is like an infinite sheet. Okay, so here the plane is intersected by all the axes, you can see, so that we get the V's indices as well as Miller indices as 1, 1, 1. So these are the three different lattice planes possible in simple cubic lattice. Looking at this diagram, you can understand a more elaborated picture. See at the top, you can see this one is that of the primitive cubic lattice. Here, two unit cells are shown. For example, you take the first diagram, this one. Two unit cells are joined. There are two cubes, so that this 1, 0, 0 planes are shown 1, 2, 3. There are three planes which are parallel. It will continue. That's why I said the lattice planes are infinite and they are parallel, equidistant. So 1, 0, 0 planes are like this. And in the second diagram, you can see the 1, 1, 0 plane shown. There are two planes shown, and it can continue in other unit cell. And 1, 1, 1 planes are also shown here, 1, 2, 3, and it will continue. So the three types of lattice planes are shown in primitive cubic crystal in a more detailed way in this diagram. Okay, now regarding lattice planes, another important aspect to be understood is what is called interplanar distance. I told you that these planes are equidistant. So what is the distance between two consecutive planes? It is obtained by this equation. Basically, the equation is for crystal systems which are having orthogonal axis, that means alpha equal beta equal gamma equal 90 degree, we can have we can derive an equation like this, that is 1 by dHKL. What is dHKL? The distance between the planes which are having the Miller indices HKL. So we indicate the particular plane as a subscript for D. So 1 by d square dHKL square is equal to h square by a square plus k square by b square plus L square by c square. This is the basic equation. In the case of cubic system, what happens? A equal B equal C. So this equation will now reduce to what? H square plus k square by plus L square whole divided by A square, because A equal B equal C. Now taking the reciprocal, what do you get? D square HKL is equal to A square by H square plus K square plus L square. So taking square root, you get this equation, that is DHKL equal A by root of H square plus K square plus L square. You need to learn this equation. This is important. We need it for calculations. Using this equation, we can calculate what is the distance between consecutive planes for various crystal planes. Let us do it for primitive cubic. Look at this. Simple cubic or primitive cubic lattice. Let us calculate the interplanar distance and also the interplanar distance ratio. That is, first let us work out what is D100. Okay, what is the distance, interplanar distance for this plane? You can easily get it substituting this equation. That is, you get A by, substitute the values of Miller indices. So what is it? Root of H is 1. So 1 square plus then 0 plus 0. So what do you get? It is A only. Right? Now, for the next plane, that is D100. So we will write D110. Alright, D110 is equal to, what do you get? A by root of 1 square plus 1 square plus 0. What do you get? It is A by root 2. Then the last one, that is D111. What is the value getting? You can now straight away tell. You can easily get it. It will be root of A by root of 1 square plus 1 square plus 1 square, that is root 3. So we got the interplanar distance for all the three planes. Now we can get the ratio of these three values, that is called interplanar distance ratio, which is a characteristic value for each type of lattice. A lattice can be identified using this interplanar distance ratio. So that is written here. D100 is to D110 is to D111. How you get this value? We can write it. It is equal to, what is D100 we got? It is A is to D110 is A by root 2 is to D111 is equal to A by root 3. Right? A by root 3. So cutting A, you get 1 is to 1 by root 2 is to 1 by root 3, and that is what is 1 is to 0.707 is to 0.577. So this value should be noted. So for primitive cubic lattice, the interplanar distance ratio for the three planes is equal to 1 is to 0.707 is to 0.577. Now we can quickly go to other planes. Look at this. Now you look at BCC, that is body-centered lattice. See, you have to be very careful here. What is the difference from primitive cubic? There is an additional particle at the body center. You can see in this diagram below, two unit cells are joined here, and compared to primitive cubic, these three planes are just like this one. Okay, so that's 100 plane, but here the body centered particle, you can see there is a particle at the center of the cube that is not included in this 100 plane. So we have to draw a new plane, and that plane is midway between two adjacent 100 plane, that is this plane. It is in this plane the body centered particle is occupied. So this is a new plane in between two adjacent 100 plane. So what is the notation for this plane? For this plane, the V's indices, the intercept will be half because it is a by 2, right? So half and remaining parallel to the other axis. So it is V's indices are half, then infinity, infinity. So what about the Miller indice? It will be 2, 0, 0. So in BCC, the plane is 2, 0, 0 instead of we write 1, 0, 0. Okay. So there are such mid planes in between all the 1, 0, 0 planes. So in effect it become all 2, 0, 0 planes which are parallel to each other. But in the case of 1, 1, 0 plane compared to this one, comparing this one in BCC and this one in simple cubic, you can see that the body-centered particle is included in this 1, 1, 0 plane itself. There is no need of representing a new plane. You understand? Because the body-centered particle is already included, contained in this 1, 1, 0 plane. So in BCC, the first plane is 2, 0, 0 and the second plane is 1, 0, 0, 1, 1, 0, just like in primitive cubic. Whereas in the third one, that is 1, 1, 1 plane in primitive cubic, if you compare with the body centered, you can see that here there is a new plane which is to be included in between every 1, 1, 1 plane. That is, in between two 1, 1, 1 plane, the body centered particle has to be represented in a new plane which come in between, like this. Okay, similar to the 2, 0, 0 plane. So here also the intercept come as half, since all the plane is cutting all the axis, the intercept will be half, 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 or the Miller indice is represented as 2, 2, 2. Right? So here also there is a new plane coming in between. So in short, in cubic, in body-centered lattice, you can see here, in body-centered cubic lattice, the planes are 2, 0, 0, 1, 1, 0 and 2, 2, 2. Here also we can easily calculate the interplanar distance and the interplanar distance ratio using the same equation, right? It's very easy. Using this equation you can do it. For example, first one D200 will be what? A by root of 2 square, that is root of 4. So what you get? You get A by 2. Then D110, so this is A by 2. Okay. Then D110, it will be what? A by root 2. A by root 2 as before. Then D222 will be what? It will be A by root of 2 square plus 2 square plus 2 square. It will be root of 12, that is 3 into 4. So it becomes A by 2 root 3. Okay. Now taking the ratio of the 3, A get cancelled. It become 1 by 2 is to 1 by root 2 is to 1 by 2 root 3. So multiplying throughout by 2, it become 1 is to root 2 is to 1 by root 3, and it comes to this value. 1 is to 1.414 is to 0.577, and this is the characteristic interplanar distance ratio for BCC, right? Now finally on to FCC. Let us come back to this diagram. You can see here in FCC, similar to the BCC, here also in between 100 plane you can see a new plane is appearing in between adjacent 100 plane, that is 200. So you can see that 200 is the first plane, and then Compared to 110 plane in primitive cubic, here also you can see a new plane appears. See, these are the two adjacent 110 plane. In between there is a new plane. So it is to be 220 because intercepts will be half infinity. So it will become 220. Right? And but interestingly, this 111 plane in FCC, you can see that all the particles are already contained in the 111 plane. There is no new plane to be drawn. So 111 plane remains the same as that in primitive cubic. So putting all together, in the case of FCC, the planes are 200 plane, 220 and 111 plane. Calculating the interplanar distance, D200 will be what? A by root of 2 squares. So that is A by it will be A by 2, right? A by 2. Then value for D220 will be what? A by root of 2 square plus 2 square. So it will be root of 8, or it will be 2, A by 2 root 2, right? A by 2 root 2. Then finally D111, what's the value? A by root 3. Taking the ratio, you will get 1 by 2 is to 1 by 2 root 2 is to 1 by root 3. Multiplying by 2, you get 1 is to 1 by root 2 is to 2 by root 3, which comes out to be 1 is to 0.707 is to 1.154. So this is the characteristic interplanar distance ratio for face-centered cubic, right? So it is interesting to compare these three values for primitive cubic, body-centered cubic and face-centered cubic. Finally, what is the application of this interplanar distance ratio? In the coming classes, we will discuss about X-ray diffraction studies of crystals, where from you can get the interplanar distance ratio experimentally. So comparing the experimental value with this theoretical value, we can identify the lattice type with the help of interplanar distance ratio. For example, in sodium chloride, right? In sodium chloride crystal, interplanar distance ratio is found to be experimentally, the value is found to be 1 is to, the value is found to be 1 is to then 0.704, 0.704 is to, and then 1.136, 1.136. This is experimental interplanar distance ratio value. So what is the lattice type of sodium chloride? You can see that this value is comparable to that of FCC, which is there in this slide itself. What is the theoretical value? 1 is to 0.707 is to 1.154. So this value is close to this. So we can say that sodium chloride is having an FCC crystal lattice. Okay, so that's all about interplanar distance and interplanar distance ratio in cubic crystal lattices. Thank you.